Today I'll be talking about torsional force microscopy of twisted bilayer graphene heterostructures on HBN or monolayer graphene on HBN, and just trying to see how this one particular technique that we stumbled upon has enabled us to really image the Moires superlattices and atomic lattices with very high fidelity. I think I'll just pull up this pointer. The importance of twisted bilayer graphene, how it has really become very exciting, is well known to the folks in this community. But I just want to highlight some of the very key things that have made it even more interesting in the last few years. Number one, this very famous work from Professor Pablo Carrillo Herrero's group at MIT, where twisting two layers of graphene at 1.1 degrees, or the so-called magic angle, superconductivity was observed. It must be noted here that neither individual layers of graphene nor HBN are superconducting, so it was very interesting that just a twist between two layers can lead to superconductivity. And similarly, shortly after, work coming from Professor Goldhaber-Gordon's group here at Stanford that showed that again at this magic angle, if the graphene was aligned to the underlying HBN, you see orbital ferromagnetism. Again, it must be noted that neither HBN nor graphene are magnetic or have magnetic atoms or elements in them. So the observation of a zero field magnet is very interesting in its own right. These very interesting findings bring with it the first question: hey, I want to see if I've made this particular sample. I want to see what twist angle I've made in this particular sample, and that also brings with it a lot of other challenges. Number one, that the moires formed in these twisted bilayer graphene material system actually vary dramatically from a few nanometers to few microns depending on the twist angle. And no one technique is perfect for them. So if you want to image a moire that is just a few nanometers, you cannot operate with something like an optical technique where your minimum resolution may be limited to a few microns of area, simply because the moire wavelength may vary significantly within that area. So AFM is uniquely positioned to help us here, and what we really try to do is try to image these structures and see how the moires were varying over the typical lengths of a device, which are a few microns. The real problem here that comes out to be is, as one tries to make these magic angle twisted bilayer graphene devices, not every device that one makes is identical. In fact, it's very hard to reproduce a device in the 2D materials field, and especially if it involves twisting two layers on top of each other. And hence, there is a need for a technique that gives you rapid feedback, something where you don't have to wait for weeks to get simple feedback on, hey, what was the twist angle of my sample? That really opens up the door to a technique like torsional force microscopy. We were motivated by the work coming out of Columbia. This is also something that Bede shared, which demonstrated the use of piezo response force microscopy to image twisted bilayer graphene samples as well as other material systems. And we actually were inspired to replicate this work. Coincidentally, this work was also performed on a Bruker dimension icon, something that we had available here at Stanford. And as we started trying to replicate this work, we found that in our implementation here at Stanford, our success rate was very low. We didn't quite understand what we were doing wrong, and we tried to dive deeper. What we were guided by all along is, as long as there is a twist between two layers of graphene, there must be a moire present. It wouldn't be present if the twist angle is zero, that is a Bernal bilayer. But otherwise, as long as there is a twist, the moire must always be present. So how can we repeatably image this twist? And we actually just tried to understand, let's look at what we have. We were working with the Bruker dimension icon with nanoscope 5 electronics, a DTR CHAM probe holder. Some of you may know this as the TR tuner or the PF tuner probe holder. And we were working with conductive AFM tips to try to replicate the work of PFM. This is a typical spectrum that we would observe. This is on the x-axis is the drive frequency. On the y-axis is the lateral deflection signal. It was reported that twisted bilayer graphene shows a response in the lateral deflection channel of the photodiode. So this is the lateral deflection channel. What we would observe are a few resonance peaks. This is good to see that there are some resonance peaks. After picking some of these, we found that we would get consistent results, perhaps around the resonances around 1.3, 1.5 megahertz. But there was something very striking here. Number one, we would see a resonance even when the sample was not in contact. The tip was floating in air. Even though this is supposed to be a contact resonance, this was observed in air, and that raised some questions. What we also found is as we increase the tip bias or sample bias is something that is required in piezo response force microscopy. So as we would increase the tip bias, we would see that the peak amplitude here of this particular resonance or of all of these resonances actually would linearly increase. That was something very striking as well, because if you're just applying a bias to a tip that is in air, why should the resonance amplitude increase if it is purely from contact? And that really made us think that this is not a resonance coming from contact, and we should stop calling it contact resonance. And we started discussing with Bead, hey, we are seeing these results. Could you also take a look?